Thank you. I was just checking if it is. Did you include or plan to include the equation for the particle in the box?
Will include.
And today you'll draw it with this little board and explain to everyone.
All right. Fun stuff. So I'll be talking mainly about so basically the whole point of this talk is to talk about perovskite. They're a recently brand new crystal structure in the world of nanomaterials due to the fact that they've shown to have high quantum yields. So the beginning of my talk has a little bit about solar cells, but that's not the main point to it. The reason why I included solar cells is because that's also an emerging area where they're gaining a lot of interest, not just in light emitting diodes, but also in the world of solar cells. So, excuse me if that sounds kind of a little confusing, but why did I do this? Because the world of solar cells and photovoltaic and light emitting diodes, they require opposite trends. So usually when it doesn't work out so good for a light emitting diode, chances are it has better properties for solar cells. So there really is no wrong way you can go down this path. But anyways, so mainly I'll talk about introducing what perovskites look like, what they are, background, and a couple talks on quasi two-dimensional perovskites. So, as I mentioned, they can both be used for solar cells and light emitting diodes, depending on what your focus of area is. So, for solar cells, if any of you have done any type of work on solar cells, you sort of know how this chart before. But perovskites are located right there. So, we get a zoomed in up on this, and you can see over the years, since people just recently started working on them compared to many of these other solar cells, for single junction solar cells, they have grown tremendously in the last 5 years. So that's a great thing to that. And just don't ever forget, I know the purpose of my talk is about light emitting diodes, but they also have an emerging presence in the world of photovoltaics. But so what is the difference between both of them? So for solar cells, we want free charge carriers with a long diffusion length. Opposite trends for LEDs, so as I mentioned, one or the other. Difference too is we want to spatially confine these charges with insulating layers, and thus the exciton diffusion is suppressed, and the recombination can be enhanced. Yeah.
So what is the insulating layer? Confined charges with insulating layer means?
Shouldn't we wait to let them go through so that
I don't know,
It's
is it
like
should be continuous
Monday?
or?
I don't care. What do you prefer?
I know mine isn't long enough, so I know I have some work over the weekend, so you just ask your questions. I think mine is like maybe 25-30 minutes long, so I still got significant work.
Everyone votes for interrupting him in the middle. If we will more in discussion.
Sorry about that if I'm interfering.
No, you're good. Yeah, I'm sorry I didn't specify that either. I know mine isn't long enough yet, so.
So you're saying that you especially confined charges with insulating layer means? Can you elaborate this something? I don't know.
Yes. So insulating layers, more like surface passivation. So you know, like how in most light emitting diodes or solar cells, they're layered with other type of materials. Perovskites is just a single layer, and you just want to passivate that certain layer within the schematic of the device.
But then if the insulating, how do you get the electrons in if in or out if you're in a solar cell, and how do you excite the material if it's insulating? And I don't think in PV you have insulating layers, because you have to have the band alignment correct to have a cascade of energy to separate your charge carriers.
Okay.
Perfect wording. I cannot say it better.
I guess I got my wording on that one wrong. Yeah, I changed that. Thank you for that. Perfect. So it probably wasn't supposed to be on the slide. It was just more.
And
trying to keep-
also, I have one comment on this slide.
Yeah.
It's kind of literally first slide of informative slide in your talk, and you talk a lot of different technical terms here. Nobody knows anything. Very hard term like the exciton dissociations. Nobody knows what's the exciton and dissociation.
Okay.
I think you need maybe 1 or 2 slides before that to talk about what is the
Just talk about terminology or separate.
And even I don't know what is the PB in this case.
Oh,
I know
what
that,
it
but I
entails.
don't know.
Oh yeah. I forgot to change the title to not include that yet. But yeah, I was supposed to say it out word, then put in parentheses.
And you mean the P photovoltaic, and again you are saying solar cell. It's not a big change, but it's kind of a little bit weird.
It's confusing.
It's not. Its terminology is right, but when your title is photovoltaics, in your slide there are no word photovoltaics, and in the slide you are saying solar cells. It would be better if you use the similar term.
Okay. Yeah.
And then I had a question about the long diffusion lengths.
Okay.
So you're saying that LEDs, you don't want long diffusion lengths, where PVs you do.
Yes.
So then it comes back to the question, how are you exciting your LEDs? Are you trying to have a current go in and you have electrons go in and then they recombine? Or is it like you have a capacitor and you have voltage going through and that excites it? Because if it's the first one where you have charges going through, wouldn't the charges need a long diffusion length in the material in both cases?
So in one of the papers I was talking about, or they
Is it cited?
it's later on in the talk, but they excited the photovoltaic or the perovskite light emitting diode with it's called ultraviolet excitation. So they just shined ultraviolet light through the material, and they got an emission off of it. So
But are you going to create ultraviolet radiation in an LED to excite your material to make a light?
that's not preferred, but
Because then it takes more energy to make ultraviolet, and then you're releasing the energy as heat to make whatever color light you want. And if it's not absorbed by the material, then you're irradiating people with ultraviolet rays, giving them sunburn inside.
yeah, I didn't think about it like that. But
It depends on final application. Maybe he wants to get the blue color light from that diode. Yeah,
That's
not a red color. Yeah.
Okay.
yeah, thank you. I'll look into this.
Oh, we don't comment. Not today, not actually. How do you do have ideas, not only on content of the individual side, but also on reordering slides in more logical sequence with if and provide some minimal argumentation, like private opinion of myself. I would start from like slide with perovskite structures at the very beginning. But maybe Daniel has different logic. Everyone has different logic suggestions.
Okay. So a couple words I'll throw out a couple times too is external quantum efficiency. To put it bluntly, it's just how efficiently the device converts the electrons to photons, allows them to escape. So, other words, how an LED works. So
How can you convert electrons to photons?
how can you convert electrons to photons? Through recombination, radiative recombination. So during the process, light is shown, or light is given off.
Well, I think this is a case of bad wording because you don't really convert the electron. You don't lose the electron. You use the electron to make a photon by recombining it.
So what is converting here actually?
Bad choice of words.
No, I mean, something is converting to the light, but what is converting to light?
What is converting light? Absorption of the electron, or relaxation of the excited electron.
So it's kind of on this page, this slide, I think, right?
I'm not sure what it's like. You don't know what it is. It may be questions.
So I think his question is what process is doing this?
But you got a light energy from where which energy is converted? It was before converted to the light energy.
What energy was converted for light energy?
We'll talk about that now. And I have a question here. Why you put this image here?
The image of LEDs.
I mean here, those are LEDs?
Those are not LEDs.
No, that's
Those are definitely not
incandescent.
LEDs.
Oh. Thanks for that.
Those are Christmas balls.
Incandescent light bulbs. Whoops.
I'm not asking what is this bulb.
Thank you. Thank you for that. So yeah, so what do perovskites do for LEDs? Not those, disregard that image, it don't exist no more. So current LEDs are pretty expensive to form or to create because they require really high temperature. Well, they're made under extreme temperatures. While perovskites, they're usually done much easier. You can buy the precursors. One of the easiest methods to make them is just drop casting. It's literally just buy the precursor and drop it onto your material. So that's also the part where it comes into with a facile synthesis. So synthesis is really easy and simple. It's not anybody can do it. You can do it in a general chemistry lab if perovskites do become cheap at that certain point. But what makes them also really special is a band gap that is easily tuned to however you want, depending on your chemical makeup of the structure. Emission of the light is really intense. Yeah.
So since you are talking about LED, since it's expensive, what materials you use right now to make LEDs and how they make and why is it expensive? I don't know really.
So what makes LEDs expensive to create right now is because common LEDs right now, they're made under 1500 Kelvin. So that's a huge
what
energy.
material they use?
Huh?
What materials they use?
What materials do they use currently? I didn't know that. I just read that they.
But you've mentioned some materials in your abstract that the whole department has already read.
Yeah. Because you are going to change that materials to perovskite to make it feasible, right?
Yeah. So silicon and gallium arsenide. Goes back to when I said that they're made under extreme temperatures.
Is it temperature is the only reason to make it expensive?
They're also made under vacuum. So
In industrial, 1500 is not that big temperature, I guess.
Well, what makes these cheaper too? Since you can drop cast them, you can make them over a huge area much cheaper than you can make these in huge quantities like you can.
But if it's silicon, you can drop cast silicon, you can put a photo bleach and all of that, can't you?
No. What Daniel is telling right now is a really great idea. It's one of the main reasons people are pursuing perovskites. But it needs to be more backgrounded with maybe references and more pronounced. But it is a really great idea. So silicon is to purify when melts. And melting semiconductor to you cannot do it at kitchen or in it's really hard. And then when purified silicon, it is cut on the chips, right? But you cannot make silicon chip bigger than like 6-inch diameter, and then they are cut it for elements. And if you have seen solar panels, they usually are like little tiles put together, because each individual crystal, if it breaks, it will stop working. So you cannot. But perovskites, they are prepared almost like a painting. You can take a wall, paint it, well, with some additional layers. No restrictions, or much less restrictions. So it is some benefits for processing, for creating large areas.
Yeah, that's a very important reason, I guess. The temperature is not a big thing. You mentioned several times just temperature, so that's why.
Temperature is also because the following has not been yet implemented, but hypothetically, silicon cannot be made outside. You cannot like paint silicon on the walls.
Yeah.
The perovskites, they do not need extreme temperatures, so you can go outside to windows, paint them, and then just use the hair fan to ramp temperature to activate them. So it could be really breakthrough in technology.
Going back to one of the things that Dimitri said, we're on slide 8, and as of yet, I've not seen one reference. So how do you know that?
I didn't think I had to reference common knowledge.
So
No,
it's common knowledge. We want free charge carriers with large diffusion lengths. Is that common knowledge?
I thought it would be for most people that study this field, but yeah.
But this is for general chemistry, right?
Make it accessible for freshmen.
Okay.
In the previous slide, you may need more than 4 or 5.
And have you seen the grading form that committee members
There are lots
So
of comments.
there will be question how good candidate operates with literature.
Okay.
So if you just blindly put, well, I'm telling the cheating way that you shouldn't do, but if you use the same reference and just copy paste it on each page, Levi probably wouldn't notice it.
No,
Right.
but
It's better to have appropriate references, but by a format. Each slide should have a reference at the bottom supporting what you
but
present.
I guess in secondary seminar, people pay attention on the reference mainly because many people here. Because reference is a big part. It's kind of literature review things. Yeah.
And it should be visible also. So don't make it like too font, where it's like nothing, because that's another way you can get around it.
Yeah, choose a style and continue the style in all slides. Yeah.
No problem. Easy. Simple fix.
It's not easy. It takes time.
Did anyone notice that these lamps are incandescent?
Yeah, that's
Yeah,
what
that's what-
he
That's what we
says
call
right away.
version here.
But I guess he does say is over incandescent like sources,
Well, there's advantages to them. Yes.
so it might be fine.
I can get away with it. So yeah, the emission of light is intense. So there's numerous advantages to incandescent lighting. So these will have due to the fact that perovskites will give off less heat than incandescent lighting. An indirect benefit of that is the reduced spontaneous combustion that you will find in perovskite LEDs compared to incandescent lighting, just due to the fact that less heat is given off. So also efficiency is greatly improved when compared to from perovskites and incandescents. So something you can hopefully move on from. So there's currently a couple of challenges for LED applications. Currently at the moment, some of the energy is lost due to leakage just currently just slipping out. Low luminous efficiency, so that just means we don't get as much light back as we should. The rates are still low, but it's still a new material to be working with. So recombination, radiative recombination. If you don't know what that slide is yet, or I mean, if you don't know what radiative recombination is, I'll give a little 30-second demo on how that works. But so another thing too is how radiative recombination works is these electrons and holes. They're not optimized yet, so there's weakly binding. They bind weakly to each other, so that's one major process to how radiative recombination works.
In a previous slide, you mentioned that perovskite is an emission of light is intense.
Yeah.
And in this slide, you're saying the low luminous efficiency. So
Emission of light is theorized to be high.
How is two contradictory things happening? What is the luminous efficiency you mean in this case?
That goes back to, well, so current materials, they don't have the highest external quantum efficiencies. A recent paper just published, well, the recent paper that I'll be talking about later, they have an external quantum efficiency of 14.3%. So 14% is not impressive in any means, but it is comparable to standard, to conventional LEDs are on the market. So that's what I mean by low luminous efficiency. It's not high, but it's working. We're working on that.
What's the internal efficiency?
Internal?
Because you can have the light reflected back into the device, which is why a lot of people look at both external and internal efficiencies. Right?
Sure, yeah. So I didn't know that internal was that part. But, well, I mean, externals outside.
So could this be that the external efficiency is low, but inherently the materials have a high emission?
Refractive index, maybe, yeah.
Or is it just due to the device's junk? Or relatively low compared to if you just have a wafer of it?
Well, in one of the papers that I came out that I read, when they tested the luminous efficiency of the perovskite, they ran it against 60 devices, and the champion devices where they came out, or the champion device, or well, the best efficient device. So where the EQE was the highest, or external quantum efficiency was the highest, was 14.3, but they were getting up to some that was low up to about 12%, 10%. So it was just they had a histogram of it, but yeah, the highest they found was 14.3%.
So this low luminosity efficiency is from a paper?
Yes.
Okay, then you probably should cite it, so that if someone asks, why is it contradictive, you can say, oh, in this study they found this, and that's why it's low.
Yeah, you need the 4 reference for 4 different bullets. Or maybe
So
maybe
reference for
only
each bullet?
if you take from the different papers. Yeah.
Okay. Okay.
Let me summarize this comment because it is before it is too late. So, from point of view of committee, one of the major goals of this presentation is an exam of candidate being fluent with literature. Fluent with literature, not in the way that you read and got your own impression, in a way that you can compare. You can specify which sources are there. So if you glance through like 60 papers, you're expected to cite all of them here.
Okay.
And if it is not important, you can put it on the backup slide, or just sided until it's not interesting. But if do not step on your own foot. Show how much you are reading. Do not hide your accomplishments.
Okay. Yeah. Okay. Cool. So if you don't know what radiative recombination is, I have a little movie to show you because movies are fun to watch for everybody. So how electron relaxation mechanics go is you have an incoming light or excitation of the electron to a vibrational state, correct? And this process is called absorption. It's how electrons get excited from the ground state to an excited state. So there's also a process where they start to relax down to the frontier or the lowest excited state. Sorry for that word. So this process is called non-radiative transmission. These give off a small amount of energy due to the relaxation of vibrating. So it's a process when it relaxes down from the excited state back down to the original ground state. This process is called fluorescence, and because of that, we get an emission of light. So
can I, if Dr. Rogers will be in the audience, he will highly likely ask you what is the difference between fluorescence and luminescence. So be careful with words. If you do not know which of these two, tell just emission of light. But be ready.
Be ready for that.
He knows that, I guess. Yeah. He knows that the difference. Yeah, we talked about this.
But are you sure that it is fluorescence rather than luminescence?
I thought that the fluorescence was just the relaxation.
In what condition it would be fluorescence? Yeah.
What condition?
In this scenario, just put some conditions to make it fluorescence.
Just at the slide.
So I'll give you a hint. It deals with the spin of the excited and ground state.
Make it complex.
So I guess they both need to be in the single state. Yeah. Yeah. I didn't include phosphorescence because it's sort of the same process, but instead of you have a intersystem crossing, because of the different multiplicities, spin multiplicities. So
Intersystem is the two system from where to where. Now it will give you answer. Yeah.
from single to the triplet.
Mm-hmm.
And then, are these actually vibronic states, or are these excited states?
Guess I could probably put excited vibrational states to make it more clear.
So
Just
then,
like this
this is all happening on one potential energy surface. Okay.
Yeah, I'm just trying to show off the mechanisms in case somebody doesn't know how radiative recombination works.
I'm not sure if you wanted to show it. Maybe it was a sequence of several electronic states.
Yeah.
Because in that case, if you're in the harmonic oscillator approximation, all your vibronic states should be equally separated.
Fully separated. Yeah, I didn't really. If it helps to make it more or equally separated, I can fix that real quick.
No. You shouldn't. It was a provocative question. You shouldn't agree immediately. You can tell. No, you're wrong. I don't like this question.
Yeah.
It's everything is opposite. It's electronic states.
Electronic states.
But think yourself. Do not follow Levi. Do not follow me. Develop your own opinion, and be ready to defend it.
Okay.
Just tell him that he's all vibrating.
People may provoke you, and in verbalization of question may decept you into wrong direction.
It's true.
Yeah. Cool. Thank you.
Especially on exams.
Especially exams.
So these are vibronic states, though.
Yeah.
Okay.
I have one aesthetic solution. Like you can change the color of the arrow accordingly. to make
Change it to yellow. Color
because
what?
in your slide they have one condition like EA is greater than EF.
Oh yeah, you didn't let me. Oh yeah, I didn't finish yet. We got discussion.
So according to that conditions, you can change color too.
Oh, I see what you
It
mean.
will look good, yeah.
Yeah. So remember when I mentioned the non-radiative transitions?
Oh,
So you remember those?
but don't do that. It will give you the wrong impressions to people because
Oh, I just wanted to bring that into attention because let me finish. Let me finish.
no, I'm not talking about this for a slide. Was circulating the electron.
Yeah.
Who part?
No, I was just trying to bring attention to that. I wasn't trying to show that.
Maybe not in that way.
Yeah,
Just try
but-
to-
From that way, whenever we saw the remember the energy that was lost in non-radiative reaction. So because of that, the energy from the absorption will always be greater than the energy of fluorescence. I was just trying to bring attention to that non-radiative transition again. So if you don't want me to show the arrow spinning, that's fine. I'll try to show off another way to bring audience back to that topic again. But yeah.
I have a question. So what's
Yeah.
the difference between transmission and transition?
What's the difference between transmission and what? Transmittance?
Transmission and transition.
Verbally, you told transmission. In writing, you told transition.
So what's the difference?
So transition is just, it goes from one state, one vibrational state to another. It's just transitioning states. And I think, did I say transmittance? Transmittance is just the transfer. So
Adhere to this.
It's also transfer.
Just say you used the wrong word. So just say you used the wrong word.
I'll probably end up using the wrong word a lot of times.
But he's a native speaker. He knows the difference between transmission and transition.
I learned Spanish first. I didn't speak English till I was 10. So yeah.
Okay, whatever.
Yeah.
Make it longer.
Don't get bogged down into semantics or arguing semantics with
Yeah.
people.
Because
Just say what you're trying to
lose.
say and move on.
Okay. Yeah.
Okay, different types.
So there are two types of recombinations. Radiative recombination is what we're looking for, is what we want, because we get an emission of light. Whether you want to use it for photovoltaics or light emitting diodes, either way we want. So non-radiative recombination is what we don't want. So when I mentioned earlier about the emission of light, it doesn't always happen that way. Sometimes we just get a phonon. The phonon is just a source of heat, and that's where the energy goes instead of a light transmittance. You look like you're confused.
Well, I don't get the first this sentence.
Which one?
When photons are present, they can be absorbed, photovoltaics, or generate a pair of free carriers LED.
So when I mean by absorbed, don't you want to absorb the energy?
Or maybe absorb, but then why in the parentheses is the photovoltaics?
Because is that what you want for photovoltaics? You want to absorb that energy for energy, or to create
And then LED?
LEDs?
You want free carriers in LED?
Yes. Peak.
You want to emit light in an LED.
Well, you want the free carriers because
Look on your
It's
slide number.
this sentence that Jabit is focusing on is very deceptive.
very deceptive.
It's split on two. I'm not a native English speaker, and what my teacher told, like, if you are feel that sentence is too long and no one understands it, just chop it on short sentences.
Okay.
So for PV, photons are absorbed. Period. For LED, photons are emitted. Period.
But not a free carrier, right? I'm not sure.
And then the third sentence.
Oh,
Due to recombination of free carriers, photons are emitted. So chop simple ideas in short sentences.
Okay.
Because right now, one can guess and try to track down what you were thinking. Like, there is something common in LED and PV because they both deal with photons. In one case, they are absorbed, in another, they are emitted. That's too complicated. Chop.
Okay. Yeah, no problem.
And then, why do we care about recombination in photovoltaic devices? Because don't we want to split the charge carriers and then they won't recombine? In the sense that they won't make a photon?
So the energy comes from the photons, is what you want.
Yes, but this is different types of recombination.
Yeah. Well, there's two types of possible recombinations.
But how absorption is related with the photovoltaic? Directly related. You just put in the parentheses. That's why.
How is absorption related to recombination?
Mm-hmm.
So, my back diagram, whenever it drops back down, that's sort of it recombining, or then that's how you get the emission of light. So that's how energy comes back from photovoltaics.
But in photovoltaics, we want to split the charge carriers, making an electron hole, which then will go through your circuit, do whatever work you want done, and then they won't recombine to make a photon. All the energy will be consumed by the work you do. So you decrease your voltage of your system until they recombine without any photon.
I guess he did a mistake here. He wanted to say if they recombine, then you will get light, that's LED, and if the carrier is separated, they don't recombine, that's for photovoltaics.
Okay.
Maybe that's what you want to say, maybe, is it?
I guess so. It makes sense.
So he's not talking about recombination, don't talk about absorb. You already, they have nothing about absorption.
So I shouldn't even show that diagram either.
No,
the
diagram is
diagram's
fine,
fine.
everything is nice.
Okay.
Everything,
It's just
yeah.
The wording?
words behind
Just
it
what you put the
are
word.
kind of clear.
Okay, yeah. Yeah, not a problem.
So, okay. So, what actually is the is there a difference between the different types of recombination other than just the energy gap between states, or is there something else going on?
Is there anything different between the recombinations?
Like, is that other than like the differences in energy between the states? Like in non-radiative, there's a middle state that cuts the energy gap in half.
Yeah.
Other than that, is there anything different about these recombination?
Other than the emission of light and or the other one's an emission of heat, I don't
So,
believe
like-
so. I believe they're pretty much the same thing, other than just one gives off heat, one gives off
What?
light.
Well, why does that happen?
It's just a random occurrence. It can either go down one way or the other. The whole purpose to LEDs and photovoltaics is try to minimize that, but through different passivation methods and etc.
Okay.
Does it have to deal with the oscillator strength of the system? So if your lowest state is optically active, one might occur and the oscillator strength is nothing, then the other might occur. Because the oscillator strength is the measure of the probability to go from one state to another. Which, if you have a defect state, then typically your oscillator strength is pretty low. Is it have to do with that, or is it just a random occurrence and we don't know what happens?
It's just a random occurrence. I don't think the oscillator strength will have an effect on it. It's just.
Oh, you wanted to show an equation for oscillator strength.
No, I asked him because he said that these two process, if it's optically he said it's random between emitting light or if it will produce heat. And I said,
Random? He told us?
he said random twice.
No, it's competing.
It's competing.
And then I said it
One
is
favorable to the
anything
other.
to do with optical activity. And then
Oh, what? Write down an equation for oscillator strings.
I don't know.
You
but
took
I'll-
advanced quantum theory from well-respected professors at first year. It's a part of exam. It's a basic knowledge
Uh-huh.
that every undergraduate
I don't know what
gets fired if not writing this. Huh? Yes.
Oscillator string.
He's in a committee member. He's a part of exam.
Yeah, no.
that's Svetlana was.
Spilana is too.
Oh, both of them are.
No,
Yeah.
that's
Oh,
that's
you're very lucky that you
yeah.
have two computational people as a exam.
You can write right here.
You are on camera now.
I'm a common? Oh, okay. I don't even know where to begin. It's been a while since I.
Levi will help you.
So, do you know how to get an expectation value?
Expectation value? No. It's been a while.
Can you write down something that will specify the quantum state of your system?
Specify the quantum state of my system. Look, can I just write like n equals 1? Quantum state, right?
Sure. So in quantum mechanics, how do we describe our system? In terms of math, with a spatial distribution.
Wouldn't just be h side is equal to each side?
So a wave function,
Yeah,
right?
yeah, wave function.
So how do we write a wave function? Maybe on the far side, the other side, yep, yep.
The left side, right side?
Right side.
Right side. So, wave function.
And let's do it in bracket form. So line, side, side.
Oh, that's what you said. Saying that? Oh, that's
No,
pretty
he
hard,
said
right?
bracket notation.
Like
Dirac notation.
Dirac, sorry, yeah, Dirac. No, that was,
Oh, that's fine.
erase the second
no,
side.
Let,
and
let
put
him do that. Wait.
Caret.
No, we got it.
Say carrot?
Like angle of bracket.
Oh, okay, yeah.
Sorry, the other way.
That way?
And remove the comma too. So that is your wave function, right?
Okay.
So now we need to make it somewhat like a probability, right? Because we want to go from psi 1 or psi I to psi f, right?
Mm-hmm.
So if we're in Dirac notation, how do we conjugate the final state?
Did you get the final state?
Because quantum mechanics is all matrix operation, right?
Mm-hmm.
So this is a vector,
Okay.
like this. We want to make another thing like this so we can have an operator in between. So how do we go from a column to a row vector?
Take something position and time? Or
So all we have to do is write the same thing but have
backwards?
the caret or that psi line, right?
Yeah, so you just want me to flip the carrot with
Yeah, so on the other side now, no, that's a density matrix. So on the other side of the line, so
Yes.
left, leave a space in between,
Okay.
and straight line. And then do your wave function. And then
Close.
less than,
Less than? Oh.
that's greater than. Okay, so if we do this, this would just be the overlap, right? Probability.
Okay.
But now we need to get an expectation value. So what needs to go in the middle?
A variable? I'm guessing.
Not good start.
Yeah, a variable, but what does the variable stand for?
What does the variable stand for? The amount of overlap between?
Wait. Do not try to satisfy person who asking you a question. It can be deceptive. Look back to your many years background in quantum theory.
In quantum theory, many years?
Yes. Classical variables are replaced by.
Yeah, I never took classical physics.
You do not need classical, you need quantum. So, in classical variables are replaced by.
Yeah, I don't know.
Hamiltonian is example of.
Operator?
Yes.
Yes.
So each classical variable observable is replaced by an operator. So now Levi can continue.
So now we know that the center has to have an operator. Do you know what operator?
Position operator, I guess.
It has position, yes. But if we're trying to go from the excited state down to the ground state, and we're transitioning down, we need some operator there, maybe
Light to matter interaction operator in dipole approximation.
Yeah, I've never heard of that.
Do not tell it.
Yeah.
Do not tell it in public if you want to stay in the school.
transition dipole operator,
Transition dipole operator.
right? Because we're going between,
That's
and Dimitri gave a nice hint, dipole, right?
Yeah.
So the initial thing, your position is correct because the transition dipole operator has position in it, but there's constants that you would miss, right? So a lot of times that's just mu with a hat.
U and a hat.
Yep, and then that's proportional to oscillator strength.
Proportional to oscillator string.
Actually, the square of this is proportional.
Well, oscillator strength is square of this.
Yes.
So you square this whole thing.
Yeah.
And then that's equal to oscillator strength.
On the better use
Sigma.
like F.
Sigma.
I never heard.
No, he wrote sigma.
Yeah,
I
but
wrote sigma. Sorry.
use some other like F.
F.
Use underscore oscillator strength.
Oh.
Yes. Yes. So that's oscillator strength.
Oh.
Very good. Very good. And the states should be different, right?
Mm-hmm.
You may want to include this equation into your slides, and either show or skip it depending on mood of the audience, but have it.
And I might be wrong, but if we went back to your slides,
Yeah.
the one that emits light, this F should be large. The one that does not emit light, F should be low.
Oh, so you're talking about this one?
Yeah, so the one that emits light will have a very high oscillator strength
Okay.
because the probability is very high that it will transition from the excited state down. Where if you have a defect state, typically those are localized states. So then the overlap is relatively small, which then means that the oscillator strength is low, meaning that the probability is very low, so it's not really emitting light.
Okay.
Does that kind of make sense?
Yes, it helps a lot.
Yeah, so it's not really a random process.
Yeah. It's a competing process, but that is dictated by the oscillator string.
Among other things, but yeah.
You're very close to global understanding. So for left side for emission of photon, it's oscillator strength. For right side for emission of photon, it is non-adiabatic coupling that you already have a nice equation for. So oscillator strength and non-adiabatic coupling, they are two competing factors. And in some sense, your future research, current research, and the research that people are doing in what you review, they're comparing what is bigger, oscillator strength or non-adiabatic coupling, which can be done by computation. Make sense?
Yeah.
So it's not random, it is competition, and educated scientists should do some procedures to assess what is which process wins, which material in one material, one aspect wins, in another one, and by screening through materials and comparing which of the competing pathways wins, you can recommend a material for one or another application.
Okay. Thank you. So, explain to you really quickly on how a circuit of an LED works. So normally, how LEDs work is usually we have a P-type and an N-type junction. So this is what this is. Into the world, to try to explain it to the world of chemistry, you can have ligands as a P-type and N-type junction that interact with a certain material. So that's how perovskites tend to work, and perovskite semiconductors. So
just a comment. When you said the P-type and N-type, and then this is happened, what is this is? You just said it's a P-type, N-type, and this is what this is going there.
Oh, so okay. I see.
You didn't say anything. You just said this is happening here.
Oh, so N-type ligands or the N-type junction of a solar cell has electrons, while the P-type ligands, or in this case, they're the ligand, they're holes, so they're gonna accept electrons, and that's sort of how that's how you facilitate the recombination from what I've been trying to talk about, I guess. But yeah, better wording on that one is what you're trying to say. So yeah, so usually how it works is you have an electron that travels from the P-type from the N-type to the P-type. The charge will go back over and recombine back to where it was, and because of that recombination is how the emission of light happens in a circuit or an LED. Or you want to explain that in chemistry? So we have a conduction band or the valence band. That's usually referred to as the HOMO and the LUMO. So the lowest occupied molecular orbital and the HOMO and the highest occupied molecular orbital, where we have the HOMO is referred to as usually as the conduction band. The LUMO is the valence band. So whenever you have materials, like whenever you excite a material from the highest occupied molecular orbital, it will go over to the LUMO and recombine. It'll go back and relax down to the conduction band, so we also get an emission of light. Good.
This is more of a semantic thing, but I'm pretty sure that the symbol for the diode is mirrored of what it's supposed to be, because currently it wouldn't flow through if we follow the symbol.
It wouldn't flow. Oh, you see it right. You see it right here at the end, at the top right here, right?
No, that's
No, the
that's
diode.
voltage.
Oh,
It's backwards. It's more of a semantic thing, but someone's gonna notice. And
semantic thing. Oh, so, because that arrow's facing to the right. Oh, so I should have probably shown it the other way around then, right? Is what you're saying?
probably would be easier just to flip the symbol.
But you got this from a source, right?
Wikipedia. Yeah. But yeah, I probably check up the
Double
animation
check
on-
because there is a convention. Electrons go one way, but the direction of current is assumed where positive charges are going. Like electrons and current, there is a definition. Direction of current is where positive charges will go.
I guess that would be a problem when he showed the red circle is
Yeah.
coming through this one. It's not
It's not
that's
going
not
that way.
what's happening.
Yeah.
And this battery is creating a potential difference in these two end of PN and type. It's not just flowing the electrons.
It's creating a what?
Potential difference. Because of that, electron is flowing from this part to this part. It's not creating current, it's creating light because of these recombinations.
Not creating current?
You showed is an electron is
Oh,
flowing.
okay, yeah.
That means it's current, but it's not generating current. It's creating a potential difference.
The potential difference isn't used for light?
Yeah, that potential difference pushing this electron to
Oh, okay. Oh, thank you. Thank you for that. Yeah, I'll take that off. Thank you. I didn't. I thought in my mind I thought that's how that worked, but thank you for telling me that's not how it works. So if it helps in it, for him telling me that. Yeah, I couldn't really read that, but yeah, thank you for that comment too. Oh. So,
So, I know it might not matter right now, but when you do this,
Yeah.
how are you going to transition between the working principle of an LED to your background slides? Because if you just say, this is this, now we're doing this, it might be a little confusing. And the reason why I say this is you should have somewhat of a flow throughout
Okay.
instead of jumping from one
Slide to
topic
slide. Yeah.
and then to another topic that's tangentially related. And it's related in your mind because you know what's coming.
Yeah.
But if we're like, oh, okay, we're talking about LEDs. Oh, now we're talking about background. Wait, wasn't
Background
LED
what?
background?
Yeah.
Yeah. What are you going to talk about? Is it LED background or?
Prospects on because a lot of people don't really know what the structure of a perovskite is.
So, like, you
Yeah.
could say, we talked about the general concepts, and now let's talk about
The material
like
itself.
the material
Yeah.
itself and how we can improve the material. So now, most of you might not know what a perovskite is. Here's what a perovskite is, and it has a nice transition. Granted, you might not want to say most of you don't know, because then you could offend people that do know.
Oh.
So you could say, for those of you who don't know what a perovskite is,
Yeah.
this is what it is, and it would make a nice transition.
Good
Okay.
point.
Thank you.
I'm sure you all know, but just for consistency of notation, let me remind you.
Or to catch you all up to speed.
Yeah. Which is the same, like you do not know, and I will teach you, but without insult.
Thank you. So yeah, after that nice introduction. So yeah, for a lot of this I already mentioned it, but here is the general structure for a perovskite. We have an outside cube face. That's usually a monovalent organic cation, where for this
What is the Q phase means?
it's cube face like 6 sides. Well,
A phase cannot be cube, right?
It's a cubic unit cell
Yeah.
with a face-centered cubic unit cell.
Yeah, so that's the defined word. It's not a Q phase.
Which other phases can be there? Which other here? Remember, once when we were talking about quantum phase, you were telling like liquid, solid, and it was wrong. Now it is a little closer. For solids, there are several crystallographic phases. Phases.
face. Yeah.
So in addition to cubic, there could be like orthorhombic, tetragonal, and if you were screening like hundreds of patients, you probably run into this.
Yeah, for the most part, yeah. So
You might, if for people who will be picky, you can tell it is cubic rather than orthorhombic.
I guess it's a cubic cell, it's not a cubic phase. Yeah.
Cubic cell. Oh, okay, sorry, wrong word. So cubic cell. Yeah. So A is a cubic cell. Usually,
A is not a cubic cell.
yeah, the outside cage.
Yeah.
Yeah. Okay. So the outside cage around that holds the crystal lattice together is a cubic cell.
He just told you that it's a face-centered something.
Face.
Right?
Face-centered cubic cell.
Face-centered cubic.
Possibly.
Yeah.
I don't know if it's considered face
yeah.
cube. Like
It's called
face-centered
prostate.
cubic.
That's the crystal structure.
Sure. Yeah.
Yeah. That's prostate.
Just call it prostate. Don't even worry
That's a
about trying to
prostate
describe
crystal.
lattice.
Yeah, that's prostate. That's what prostate means.
Okay.
And this would be really good to start with this slide, rather
Yeah.
than
That's
Okay. Yeah. What's that? Sorry. It's probably the first one. So yeah.
first reference.
Yep. So yeah, wherever you see the blue circles around, that's usually a organic cation. Usually in most cases, the most common you'll see is formaminium or a methylammonium. So the B inside the octahedral cage that is formed by the headlights. The B is usually, for most cases, lead happens to be the most efficient perovskite. Lead-based perovskites are tended to be the most better ones at the moment, or most efficient ones. Well, X, you have a halide, so depending on what halide you choose, you have different properties. So this whole thing is just what a perovskite crystal lattice is. So for most part, I mentioned these already. That's just a pro already again, but a con. So what it means by intrinsic crystal phase transition, whenever you create perovskite structures, it's hard to try to keep it all the same geometric equivalent. So you'll have different types of layerings whenever you make the structure. So it's not going to be even all the time. It'll be layered. It'll be different. Certain the ratios will be different. It's not always going to be the same. So that's what hard is. Well, that's what's hard for synthetic chemists to deal with at the moment whenever they're working with these. So these are also made in high temperatures, just not at the cost that silicones are. These are usually made around 400 Kelvin, 500 Kelvin, so nearly a third of what the conventional LEDs are, and they degrade rapidly when exposed to moisture. So that's kind of hard whenever our whole world is water-based. Well, high percentage of it is water.
And the last bullet, make a meaningful sequence. High temperature is this. Just rewrite the sentence here.
Huh?
This last bullet, rewrite the sentence. It's not just high temperature. This means nothing now.
High temperature of formation.
High temperature formations, maybe.
Okay.
Yeah.
Yeah, I see what you mean. I didn't finish the sentence. Okay, yeah. Thank you.
Or high temperature relates to the crystal phase transition.
Oh, it does? Okay.
Point, yeah. Okay. Or for some of them it does anyway.
So when I mentioned about the band gap tunability, so how this works out is depending on what type of halide you decide to make your structure out of. So this was a study done with cesium lead halide nanocrystals. So they're able to get varying amounts of emission at different wavelengths due to the composition of the perovskite structure that they decided to inherit and go with. So as you can see, using a smaller base halide, such as chlorine, compared to iodide, using chlorine, we got more of the UV, or more closer to the UV range of the visible spectra, while we used more bigger ions, such as iodide, we received more closer to the IR range So when I mentioned that this was a high well, the band gap tunability is really simple when it comes to these structures. It's because just depending on your composition, your perovskite, you're able to have varying amounts of color. So
What is nanocrystals? Sorry.
Huh?
You've mentioned that it is nanocrystals.
Yeah.
What are nanocrystals? What's the definition?
What's the definition of nanocrystals? Really, really small structures that are just in really concentrated.
What does nano mean in science?
Small,
What does pico mean?
smaller.
So, what's the difference between nano and pico? Is there a pico science?
Is
There
it
are
different
science?
in
No.
ER?
Right now, pico science.
Is there a reason why?
I don't want to say it again.
So what's the distance between two hydrogens in hydrogen molecule?
Like an angstrom.
Okay. And what is nanometer? How many angstrom?
Like 0.1 angstroms.
Mhm.
Is that it? Because isn't it a nanometer is like 1 to the negative 9th, and an angstrom is 1
What
to
is
the
bigger?
negative 10.
What is
Okay,
bigger?
you got-
Angstrom or nanometer?
No, he just said that 10 to the power 9 and
1 to the negative 10th is an
so
angstrom.
then wow, how then say what's the instrument
A
then?
10, it's difference of 10, right? Well, magnitude then.
Yeah, so which one's bigger?
Which one is bigger?
Nanometer is bigger.
Okay, 10 times.
So if it's a nano particle, if you have the knowledge that it's small,
Yeah.
that means that it's on the order of nanometers.
Okay.
Compared to bulk material, which is on the order of
Angstroms?
no,
No.
like micron.
Then imagine a
millimeter.
pico materials, how small it is.
Like if you have a grain of salt, you can see that without special stuff.
Okay.
These, can you see an individual dot?
Probably not. You probably need a special type of microscope.
Yeah, so the nanoparticles, because they're on the nano size,
Okay.
right?
Oh,
Does that
so
make
you
sense?
just can't like. Okay, yeah. Yeah, it makes sense. I see what you mean now. They're really.
So I have one question, maybe it's a stupid question. So
Yeah.
why it's important to band gap tunability?
Why?
Why you need it?
Because what if we want to make street lights? You kind of need a red, green, and a yellow. You don't want. It'd be hard to make street lights out of just one color now, don't you think?
What light you said?
Street lights, whenever you're driving, if they're all the same color.
Oh, traffic lights.
Traffic lights. Oh, sorry. I have different words for it.
But you can synthesize different organic materials with different color that emit.
Mhm. But
Can't
his
you?
question was, why do we want different colors?
Yeah, but then you said we just need different color lights, so we need different colors. Organic material, you can do that as well.
Mm-hmm. But why perovskites then? I guess. Another
And
question?
don't say this straight like that's a very cheap example. We are talking about very technology system like photovoltaic and other things.
Do you have to
Streetlights made with
change?
LEDs, so it's
Oh,
Sure.
okay.
Do you have to change your material to go from 450 to 500?
Oh yeah, it has to be different composition based. Yeah.
No, it's the same. Cesium, lead, bromide 3. You have the peak at 475 and 525 about, right? So you have
the
this.
size separate.
Yes, so for perovskites, you can have the same material and have different emitting lights. Same process, super easy. Organic materials, you have to create different dyes at specific wavelengths, and they don't emit at 450, 500, 575, depending on the size. For nanomaterials, if you change the size, you directly change the band gap, which is the big benefit over organic material, which you can't do that readily.
Okay.
So I have another irrelevant question. If you want to make a digital display by using perovskite, how many different types of perovskite you need?
How many types?
How many different types you need?
Well, wouldn't you want to include? Well, if you want to make a display, doesn't the display have like millions and millions of tiny LEDs?
So you need
But-
millions different types LED perovskite?
Well, not millions, but a huge array, small ones.
No, he's not saying number.
I mean,
He's
different
asking
type. How
when
many
you
different-
synthesize these, how many different types or different batches
Size,
do you
yeah.
need to make? So if you look at your colors
Mm-hmm.
and you want to make an LED can be any color,
What is the structure of human eye? A little question from anatomy.
What is it?
Human eye, eyeball.
we got sidetracked.
We have a cornea.
Sorry, but
People.
We get sidetracked every meeting.
Not really good with anatomy.
So
They're
on the
cones.
on the back side of the eye, what is placed there?
Our brain.
Huh?
The brain.
Before brain
That little tail that connects to our nerves.
and between this nerve and actual eye, at the back side of the eye, inside.
Well, I don't know.
You have a compound that senses light.
A detector that converts photons into electrical signals that go into nerves, right?
Okay. Right. Now I do.
Same as similar to your photodiodes.
Okay.
So there are cells that are receptors to light.
Mm-hmm.
How many types of them?
A lot of them.
No.
Make it more simple then. How many different color you need to make this white color?
Do you know what RGB means?
Yes.
What does
Too
it mean?
simple.
Perfect.
What does RGB mean?
Yes.
Yeah.
Isn't it just like
Oh, still you don't
the colors be changing?
Let him speak. Yes,
So-
yes. What is RGB?
Is that just like when the colors just be changing all the time? Or-
Explain by your own words with more details.
start thinking from very simple things. Not
What about Roy
talking
G.
out.
Biv?
Just open
Isn't that
this.
just like the rainbow?
Yeah, but what does Roy G. Biv stand for? Look there and it might help.
The colors, right? In
Yeah,
the
so
order?
red, orange, yellow, green, blue, purple,
Mhm.
violet actually. So what
Basically
is
indigo.
indigos? Yeah. What does RGB?
Red, green, blue.
Yes, perfect.
So going back to Jabez's question,
Yeah.
if you take your samples, how many different vials do you need to make an LED?
I guess 3 then, right? If you just need red, green, blue.
Yep.
Well, that's good. Thank you for that. I never know that's how TVs work. You just need red, green, blue LEDs. Oh, that's probably why they made such a big old. But there was a lot of papers on green emissions then.
Yeah.
Oh, okay, that helps.
And Aaron, it's difficult to make blue light
Yeah.
in perovskites, or is it? Because I thought there was one that was difficult to make.
Blue, without doping, blue has poor quantum yields,
Okay.
but you can finagle them to
Okay.
make them bright.
Yeah, I've seen papers on red and the emissions on those are low, but I haven't seen any on blue at all, so
Yeah,
they're not as common.
Yeah, just because they're bad emitters by themselves.
So yeah, so back to that, these are also theorized to have a quantum yield of 50 to 90%. And in case you're not too familiar with what quantum yield means, so what quantum yield means is we take the number of emitted photons and divide that over the number of absorbed photons. So it's basically a ratio of how successful we get, how much emission we get back after we spend energy to excite a certain material. Any questions on that? On the slide? Yeah, I know I also didn't have a number of my slides yet, but that's just because I haven't fully worked out my slides yet.
But the numbering will.
I mean, did you answer the question, original question of Jabet? How many types of?
Oh yeah.
Yeah,
Yeah,
three.
you did.
We figure out answer.
Yeah, thank
So
you.
the right word is retina.
Huh?
Retina. For
Retina?
the retina.
Oh, that makes sense. Yeah, retina.
And it has the rods and cones.
rows and cones.
Rod and cone.
Different types of cells. Yeah.
So just by anatomy of human, the cones, there are just three types of cones. One absorb red, another green, and another blue. So all colors that we see are just superposition of different proportions of red, green, and blue.
Is that probably why whenever you go to a computer, you could they give you that little wheel of colors, you can just go select it,
Yes.
and then it tells you like the certain percentages of red, green, and blue it is.
Mm-hmm.
That makes sense. I always wondered what all that stuff meant. I just didn't know.
I'm surprised now.
So our meeting has
He's very happy.
educational power.
Yeah.
It always does. I don't. That's why I'm thankful. That's cool. Thank you.
Do you know why
Why what?
red, green, and blue are the primary colors for light?
Because it's all a certain percentage of each other. I'm guessing. Well, I just remember like in kindergarten you mix yellow and orange and got red.
That's pigment.
Oh, that's not how RGB or that works.
No.
That's a different
So
position.
light can be have duality, right?
It's duality. Okay.
So what does duality mean?
Don't push him.
So it can be a particle or a wave, right?
Particle or a wave. Okay.
And if you take red or green, you take the wavelengths and you add them together, they're constructively and destructively interfere, and you change the overall wavelength to a different color. So that's why red, green, and blue are the only three that you need, because if you mix them and you take the waves and you do the superposition, you change the wavelength.
Okay. Helps out. Thank you.
Okay. Next.
So quasi 2D perovskites.
So sorry, we do not let you speak, but you're going to go to quasi 2D perovskites.
Huh?
Quasi 2D perovskites.
Yeah.
So your nanocrystals, how many D are there?
I think they're 3D, right? They're just surrounded everywhere.
Once again, how many D?
0D.
Yes.
Yeah. They're zero dimensional. Is that just because they're so small? I guess.
Ask your wife.
That one.
That's why you had another what is quasi. What is quasi means?
What does quasi mean? It is like a varying amount of crystals. That is. It's just like.
It's not a science term. It's English word.
What does quasi mean, Levi? I know you already know. Oh, you look like you're ready to open up your mouth and say something.
No, I was gonna. So quasi means it
Intrinsic.
isn't totally 2D, but it acts as 2D.
Like some.
Oh, okay,
Right,
that makes sense
because
down there in the paper.
If we go to 0D,
Yeah.
that would be a quantum dot,
Okay.
right? And if you think back to your college quantum mechanics for chemistry and particle in a box, if you have a one-dimensional particle in a box, right, you have one well and it's only along X,
Okay.
right? So 0D material is confined on all three sides, correct?
Yes.
So 2D material is confined on one side, right?
Yes.
So that would be a table.
It elongates in two directions.
So is there any material that is a flat surface from one side of the universe to another?
Is there any material that's flat or that's two-dimensional from one side of the universe to the other?
All the way is confined on only two sides.
If the two
No.
dimension is comparatively bigger compared to the other one,
Yeah.
it's known as quasi 2D.
Yeah.
Wait. Repeat that? If one side is bigger than the other, it's not as quasi?
Everything has a 3 dimension, right?
Everything has 3 dimensions. Yeah.
A world is 3 dimensional world.
Okay.
So among the 2 dimensions are comparatively too large compared to other one. Suppose like this table.
Oh, so like just like how there's different sizes of
Suppose like
tables.
this table is X and Y is too large compared to its thickness.
Yeah.
So
That is known
I
as
know
a
that Dimitri
quasi.
has a code to do this, and it's to compute the density of states. And density of states experimentally can give you what your structure should be, right? So 2D has steps, right? So they step like this. If you changed the length of them, right? Once you get past a threshold of like ratio, it will always act 2D, right? So quasi 2D just really means that although it's not infinite, it is as close as you need it to be infinite.
For the 2 dimensions that it is.
To get a confined effect.
Yeah, for the confinement, right? So you only have one, and then it goes on, but it doesn't go forever. But the length or the aspect ratio is big enough that it acts as 2D.
Okay.
Right, Shirley?
Mm.
Right. I think
I
so.
didn't read it last
Okay.
time. Yeah.
So yeah, they gave nice sense. So in this talk, they found out in quasi 2D perovskites to be a really strong emitter of green emission, but show that in a minute. So here they used certain varying layers of perovskite structure. So the blue octahedra is the PBRB6 cage. Right here they used as the A cation, they used phenyl ethyl ammonium with a formaminium composition. So when we look at this figure right here, all the way to the left, this is the X-ray diffraction. So right here. What is that supposed to mean?
So what is the x-axis on this figure?
X-axis on this to theta
Data what's it?
or
Theta.
theta.
Okay.
Sorry.
So what is theta?
Theta. I can never say that. I always say F. Yeah.
Many people theta. So what is this theta?
It is the isn't it just like how whenever you shoot an X-ray back at it, it comes back at it. It's to tell the surface, or tell how the varying surface is, or different grains and go on forever. But it's just for structure. Well,
So
surface structure.
it diffracts at different angles.
Mhm.
Okay. And why the signals are different for different samples?
Well, as layers get bigger, they started to almost look as if they were getting 3D in shape. So that's sort of what happens right there. Right here, they took the perfect 3D structure. That's what they marked this as 100, because that peak right there is trying to refer to it as a complete 3D structure. So whenever you keep increasing the concentration of, or you kept increasing the concentration of the layers of perovskites, the peak significantly got bigger and bigger as compared to a 2D. So you're saying that the more layers of perovskites you added to it, the more 3D it became in nature?
And again, if you progress from 3D, from infinite number of layers to small number of layers, what happens at small angle, small theta?
What happens to small theta?
Yes.
Other than the structure changing, because I mean
New features pop up.
Yeah.
New features appear. Right?
Yeah, well, that's probably what happens right here. You see this peak right here keeps disappearing, and in 3D it's basically essentially gone.
So smaller smaller objects in your sample will correspond to small angle features.
Probably at the surface, yeah. I really don't know.
Let's hope that angle will be not at your talk.
He's been at every talk. He will be there.
Okay. You may approach him at the morning and check how to address these questions so that you.
So you probably don't want to mention the 100 because I don't think that's what you think it means.
Oh, they just use it as a reference peak to the 3.
Yes, but 100 does
It's not 100.
It's
It's 100.
Yeah,
It's
I,
100. Yeah.
but
Sorry.
it's a It's
Oh,
an
it's
index.
100, not 100.
What is the
Yeah.
100 mean?
It's just, isn't that just like a nanorod? Kind of? Or like,
You see that they have a parenthesis in the
I
number.
know Fatima was all about
Fatima,
it,
you
right?
should answer this one.
Look at this number. They have a parenthesis in the number. It's not just
Infinite?
No.
100. It's not just number. They have a
So it's
bracket.
Miller indices.
Miller indices?
Yeah, for crystallography.
Now you made him confused.
Yeah, I never heard of Miller indices.
You will hear them again and again.
Okay. I'll hear them again, yeah. Okay.
So you can probably just gloss over that. So don't bring up 100.
No, I was just gonna say that as you add the more perovskite layers, it becomes more 3D in nature. Is that good enough for that?
Sure.
No,
But
we're
you
talking about the
need-
number.
You don't need to talk about the 100.
Don't ever mention that. That
No.
thing don't exist. Okay.
Yeah.
Oh, Daniel, I failed. I failed to find this paper. I literally typed Nature Communications Volume 9, article number 1169, and nothing popped up.
1169 is not an article number.
The reason of giving references that people can find it.
Okay.
Who is the author?
Page, right?
Oh. Yeah, I didn't include any.
What is the title of the paper? I'm really interested. I wanted to get into this, and this information is not sufficient. Can you quickly help?
Yeah.
What do you remember, like title or name of the author?
So the title was Quasi 2D Perovskites
Okay.
for Green Light Mission.
Okay, good.
Fishing
Thank you.
and
It
light,
should
yeah.
be sufficient.
Yeah. It was a 2018 paper. There's a lot of papers on this, but this one in 2018 when they used phenol ethyl ammonium to happen to be the most efficient one. But yeah, apologize for that. But yeah, so right here they have the photoluminescence chart. So the key thing to this one is that the N equals 3 layers. So this specific one where we have 3 layers of perovskites, happened to be the best candidate for photoluminescence. It was the most it was the one that gave us the brightest emission back compared to the N equals 4. So N equals the second layer too is decent, but once again it's not the best. It's up there. It's not equivalent. So one thing too, whenever we did mention the 2D perovskite, we saw more of a UV range spectroscopy, where as soon as you started adding layers and it became more 3D in nature, it magically got shifted to the 550 range, which is in green emission. So this is one where we refer to the photoluminescence intensity and the peaks. So the red line is trying to indicate the peak at where the highest intensity is at, and the black line is just the intensity. So yeah, once again, you see that the N equals 3 composition did have the highest intensity, with 4 coming in second place, and a composition of 2, or the one layer past the 2D, that was third best. So this is a visual aid to this thing where you see that that one really hurt to look at after a while because it's extremely bright compared to the other one. So this black stuff is the doping of the phenyl ethyl ammonium. So as the more you added ethyl ammonium, the more black it got in nature, and it kept reducing. So you can see it kind of kills it after a while. So there's a certain composition that's best found for this stuff.
And also I have a comment on this reference. This
Yes.
is not the original reference. This is a reference for corrections of the original paper.
Huh?
This is a reference for the corrections of original papers.
What do you mean? What do you mean corrections?
They did some corrections on the paper,
So,
so this is the reference of that corrections, not the paper.
Suppose, like, Levi becomes faculty, and Ben becomes his postdoc. Ben writes a paper, and Levi submits it without reading. And then many people in the world discover that something is wrong with this paper, and they started to feel ashamed. But they do not. They want to stop it. Then immediately, as soon as you discover that it's wrong, you send follow-up paper with corrections of errors to tell like, oh yeah, we were in a rush, but actually we found our mistakes ourselves.
And this correction is just missing an acknowledgement.
Sorry, I didn't mean anyone personally.
Probably something I would do.
It's probably something I would do too.
Yeah, so sorry for that. I guess I got my references wrong. All I did for this reference, I just copied the bottom left of the page and just put it there. So I guess that's not the correct way to cite this stuff. Yeah, that's why a lot of these references might be wrong because that's all I did.
Follow some SW journal style. So
Follow the what? The ACS style?
yeah, that will come more.
Okay. It's not a problem then. Yeah, do it.
You guys have EndNote?
Yeah, I should probably use that. He taught me how to use it.
I
Yeah.
thought you don't have it. No, that's
Sorry.
like
Yeah, you should just use EndNote if you have it.
Okay. Yeah, no problem. So they also found out that to be able to increase the photoluminescence yield, they did it by passivating the surface with a organic material. They refer to this as a small organic molecule, but I don't consider topo to be a small molecule because it's pretty big. So it's a phosphate with basically 8 carbon chains around it. But yeah, so basically without it, the photoluminescence quantum yield was found out to be about 50%. But after introducing this, it rose up by almost a quarter to nearly 75%. So the fluorescence lifetime also increased by double the amount, which is amazing. It's beautiful. Makes me cry a little bit thinking about it. But if you don't really know what passivating it means, it just means it's binding to the molecular ligands. And in this case, since the perovskite has the octahedral cage I was mentioning to it, it was binding to the uncompleted octahedral cage. So with this passivation, they were able to get these nice charts. First one I'll mention to you is the excitation or the quantum yield. So not much of it changed. You still got the same type of emission, just the amount that you got back is the same. So intensity doesn't change. It's just how much light you receive back changed by almost a quarter. So this right here is how they tried to conclude that the topo did successfully bind to the perovskite structure. So when I refer to the black line, this is an FTIR, by the way, infrared spectroscopy. They use this black line right here. It's topo, and well, the red line is without it. It's the clean slate. With the blue line, that's the dope version. So this little broad peak over here in the 1100 range, this is equivalent to the phosphate bond. So the P oxygen bond. This is around the range that it vibrates at. And well, in the perovskite structure, this peak they're trying to conclude that the topo did have a successful binding to the perovskite structure due to this broad peak that we see here. So as you can see in the undoped version or the clean version, there was no peak visible there, but in the doped version there was. So you can conclude that there was a successful ligand binding between the two. So another quick thing to this. So non-adiabatic coupling is referred to as, you can compare it to,
I don't know why you jump here from the last one.
What's the connection? Because
I guess I didn't really
seems
have
like there's no connection.
No, there isn't. It's not polished, as I said.
But answer now.
Also, no, you can just say
how to
it.
transition?
How to transition? Well, for the most part, I just wanted to talk about how that was successful green emission. So that's a likely candidate for it. We have a high quantum yield from previous talk. We're using ethyl ammonium as a thing, but this is more of computational studies to try to model non-radiative recombination. That's usually done with solving for non-adiabatic coupling, because not everything can be answered through experimental investigation. Computational investigation helps out a little bit, and so.
So in other words, you could say, up to now, we've looked at the emission properties through experiment. However, it's very difficult to look at non-radiative relaxation. So I'm now going to go to theoretical studies to try and explain non-radiative relaxation. Right? That's what you're saying.
Yeah.
Okay.
So
That helps.
slower ramping.
Slower ramping. Okay.
Make an empty slide with maybe 2 words. Computational modeling.
Okay.
And then explain what Levi told.
Okay.
So some questions is hard to address experimentally, and theory helps. And then you don't need to write it. You can explain it by words, like how computation can help the perovskite science. And you nicely wrote it in your abstract. you need to just to verbalize it, so that computation can help to assess band gap. It can assess the oscillator strengths that you will introduce by this time in previous slides. And it can assess the electron, the dissipation of energy from electronic to nuclear degrees of freedom. And compare competition of radiative and non-radiative processes.
Okay.
Okay? And now you are looking on how to describe non-radiative processes with some very basic introductory things. So it was missed.
Yeah. Okay. Yeah. I sort of figured.
And then I had another question on the last slide.
Yeah.
So you're showing emission. There's a very, very strong peak at 400, and then there's a relatively broad peak. Why are there 2 peaks? And if you're supposed to use these in LEDs, why would you want a 2 wavelength emitter?
So I think this peak is just right here is because of the reference. I think that just happens normally whenever you do this type of
What is the
experiment.
reference happen?
Oh, so that's just the laser excitation.
Is that
Yeah.
citation?
Yeah.
Right?
Yeah, it's just it's noise. I guess if you want to compare it to like FTIR, it's just noise.
Which one is just noise? I
The
missed that
black?
one.
The reference excitation,
That's signal.
that signal. Yeah,
That's
there you go.
the
Not
light
noise.
you're putting into the sample.
Okay. So yeah, so really it's just one wavelength, not 2.
Doesn't make sense.
So they have no stock shape on the first peak and
So
it's reluxing from that. Same energy.
So the 400 nanometer is just a laser excitation.
Yeah, and it's
Yeah.
being scattered and then it's being picked up possibly. I don't know.
How can you measure it?
So
Detector?
I think,
No, it's not possible. In laser spectroscopy, it's not possible.
yeah, I don't know, that's why I asked.
You have to have a filter, something like that. I guess the initial excitation should be less than 350, I guess.
Well, they used ultraviolet excitation for to get that green light, or in the previous image.
Yeah, they didn't mention the just acceleration. They're saying the reference acceleration. What that means? They explain their things.
I don't think they did, or I
It's
would
probably in the methods, but that has to be the laser source.
Yeah, it's something there in the method. Yeah.
See, the thing is though, with this paper, when I was reading it off of Nature, they a lot of the stuff they referred it to was the supplemental information, but it wasn't included in the article.
So then you go to supplemental and you
Did
look
you
at
go
the
to the
supplemental.
There was
Oh, there wasn't.
I couldn't find it. It wasn't on the article itself. So that's what was bothering me, because a lot of
Did
the
you
stuff
look
they
on the
said.
correct
Look at the
version or original
supplemental.
paper?
Look at this. Huh? I looked at the paper that was published to Nature.
But you went into supplemental information and you couldn't find it.
Well, because you know how like you could click on whenever they cite like a little number and they tell you that you could click on it, it'll take you to the reference specifically. Can't you do the same thing with supplemental information?
No.
When
I
it's
have
highlighted?
no idea.
He's just saying that clicking on the Adobe that make a hyperlink.
No, they get like hyperlinks.
You
I-
cannot depend on hyperlink always. You need
Yeah.
to go to
Well,
download.
I couldn't find
download.
the supplemental data. Yeah, when you go to the back, it just goes straight to conclusions and references, and that's it. So that's what was a little bothering.
It's a separate file.
It's given the electronic supplemental materials.
You found it?
In the right side, it's saying the electronic supplementary materials. Look on there.
Okay. I'll look at that.
Okay, whatever.
But yeah, so I'll have to look into that because a lot of the stuff they just kept saying go to supplemental data. I couldn't find it. So
Yeah, I have a confusion on this one in the first peak because if it's the excitation energy at the 400 nanometer, and they have a one emission peak exactly the same same energy. And there are no stock shape for this one, so
no
there
shift.
No, it has to be the excitation.
Hmm?
It has to be excitation. Adam's right. Because it just says photoluminescent quantum yield of this system, perovskite film with and without top. No.
No.
And if you just look at the peaks, it's
Yeah.
the red and green one, or red and blue one are less, because that's being absorbed.
Yeah.
But
So it has to be excitation.
So it's just the point of excitation then. Okay.
Okay, now we get into the fun stuff.
Fun stuff. Computational modeling is helpful for being able to model non-radiative recombination. So this is usually done with non-adiabatic coupling. So one of the first basics to computational modeling is referred to by these two men, Max Born and Robert Oppenheimer. So Robert Oppenheimer is known for more than just creating the nuke or being the lead investigator of the Manhattan Project. Him and his advisor, Max Born, they came up together with a Max Born approximation. So this is sort of how you can find an electron in a many-body system. It's their own version of trying to solve Schrodinger's equation. So that's the first basis to computational modeling, is be able to to be able to get number of energy states. Commonly it's always referred to as orbitals, but it's just to everybody else you can call it energy states. So after whatever type of program you want to solve for this equation, many has their own things, but it would all lead to eventually trying to solve for non-adiabatic coupling. So what non-adiabatic coupling is an equation that we take into consideration the movement of electrons. So there's a certain level of degeneracy that is always found in each energy state and energy level. This sort of degeneracy is what we call it, or is what we refer to as non-adiabatic coupling, or specific overlap between both of them. So this is just trying to say the probability of being able to find an electron, or the probability of transitioning of one electron from one state to another varies within time. So that's what non-adiabatic coupling is boiling down to. So there's a diagram that I hope it might make a little bit more sense. So there's energy levels, energy states between varying. They change in time, right? And a certain overlap happens between each one, and that's how we get non-adiabatic coupling. So you could also tell it. You could also remember it back to refer this back to like early level quantum mechanics. Whenever the difference is always just by a whole energy state. So whenever you remembered how you find energy levels at each state, where It was like energy is equal to half nu. It goes like 3 half nu, and so on and so forth. 5.5. It just go off one by one. It'd be increased by 1 each time. Is there any questions on this? I know you guys have comments, right?
I don't think anyone's gonna understand this slide.
Nobody's gonna understand this slide.
Because what's Hij?
Hij, just the overlap between both of them.
So, is it shown anywhere? What
I didn't
Hij
show that
is?
equation that I should have. I just didn't want to show too much equations.
Wait.
What
Isn't there just an illustration for your previous slide?
You just take that equation and this is just the illustration.
What is this equation?
So reproduce this equation again on the next slide and explain what is what. Okay?
Okay. Explain what is what. Okay. Yeah.
And probably if you have Vij here and you need
Put
unify them.
Hij.
Or call it Hij here, yes.
Yeah. Okay.
And then can you go to the next slide? No, here.
Yeah.
So, what are these sheets?
Different energy states.
Let's go to the back slide, previous slide. So, which symbols on this slide represent those
Sheet.
I don't know how to pronounce
That's,
them.
Huh?
I always fear to mispronounce.
So which keyword is represent that rectangular things in the next slide?
What's inside here?
Yeah, which symbol is representing that things?
The side.
Or what's your variable? What's your couplings a function of?
Energy states.
What's in the brackets?
I guess
The
the
Parentheses. What's in the parentheses?
The parentheses, the position of electrons.
Okay,
It is
comma,
not
and then further. What is
What's
that?
your
Further.
independent variable?
The position of nuclei,
Further.
time.
There you go. So you. So those numbers are times.
Yeah. Oh, the time steps.
Yes.
Oh.
Actually, it's the average between time steps,
Yeah.
Time steps.
according to the paper.
Oh, did I set that
I'm
one?
doing that
right?
symbol, that's right.
Yeah, you said it right. So, Hij is not Vij.
Two different things.
Totally different things.
What is KS?
Constrom orbitals. So I guess I just took this one from what we did, but I guess I can't.
I'm not saying it's wrong.
Huh?
I'm not saying it's
Oh.
wrong. I think wrong.
Yeah. So yeah, the orbitals are from Constrom's approximation.
Levi? The average, I think it is when there are diagonal elements like HII, which Daniel doesn't show, but it is off diagonal elements. It looks like overlaps. No?
They're doing the average after the one.
It is energy.
This is not energy. It's exactly the same equation you would.
Okay,
This one.
so it's the average, not right.
Why average?
I don't know. That's what the paper says.
No, it is not average.
We
Okay.
got non-average copy
You,
for every step in the whole file, right? Real.
So a little confusion. It's better to give 30 seconds for it for Levi right now. So there is an average of. Can you go back one second?
Yeah.
So right now it is matrix element of time derivative,
Okay.
which means you will subtract the practice this expression once at time t, another once at time t plus delta t.
Okay.
But where would you put T plus delta T? To the left or to the right side? To bra or to the cat?
Okay, so, but that's still an average.
It's average only between,
Between the two,
it's symmetrizing of the couple.
Okay, that makes sense.
But the word average scares me because like it mean, we tell average when it is average over 1,000 steps trajectory. It is just symmetrizing of it compensates imaginary parts if you do this thing. So what you're showing is HIJ on the second one.
HIJ on the
Yep.
second time step?
On the next slide, yes.
Okay. My bad, I was wrong. I guess I didn't.
Oh, so that's what HIJ is equal to?
No. HIJ is same as VIJ there.
Okay.
And the sheets is your sets of Consham orbitals.
Just a conjunction.
So, what is the bracket in HI there? 1.5, 0.5, 2.5?
That's the time.
Yeah. But it's why is 0.5? That's maybe answer your question, is it because of average of these two, right?
Why is it one?
But that then brings up other questions.
You have a question? What was your question then?
Go. I mean, what is the number? Is a in other words, what is this arrow sign? This arrow mean? This big arrow.
The green arrow
No,
or the
no,
black arrow?
Black arrow. This long arrow. Aaron already answered that one. Yeah. You said that this arrow is downward.
This
arrow.
one?
Yeah.
Yeah.
What is that arrow? What is this axis?
Snapshots
Scale
of
of
different
energy level.
time steps,
Energy level. Scale
energy level.
No, it's a time step. Yeah. Okay, go on. Sorry.
Oh, okay. Yeah. So that's so non-adiabatic coupling is a pretty high level theory, and I gave you a generalized thing because you could pretty much talk about this for hours on hours on hours on end. But just know it's the spatial overlap between two time steps. So pretty much already seen this one 1,000 times. So we always want to see what happens whenever you vary the composition of perovskites. By doing that, we take a perovskite model and splice it in half. So the lead iodide rich surface is the methyl ammonium rich surface, but spliced in half of the octahedral shape that you see here. So yeah, we look at the effects of two of them, a methyl ammonium iodide rich surface and a lead rich surface. Depicted by the black circle is the lead rich, and the pink dots referring to as the iodides. Right here we see our A cation or methyl ammonium iodide. So when we take into account the partial density of states, we look at both of them. We see that the band gap in the lead iodide rich surface is significantly smaller than the methyl ammonium iodide rich surface. A great positive to this is because of this lower band gap, it takes us less energy to actually excite this material than it would if we were trying to excite the methyl ammonium iodide rich surface. So that is one benefit already over of the lead iodide rich surface over the methyl ammonium iodide rich surface. So TD right here is referred to, or tau D in femtoseconds. This was referred to as the pure dephasing function. So what it means for a dephasing function is how long until the wave function doesn't hold up anymore, or until it breaks down, until it's not correct. Right? Leroy shaking his head over there, right?
Oh, I'm not looking at that.
Oh, you're laughing at something else.
Yeah.
So yeah, that's what that means. You can see that they're relatively the same in time, so that's not too much of a difference maker right there. Couple of femtoseconds isn't too much of a difference. One of the bigger differences we see is the last two things. Non-adiabatic coupling is what the NAC stands for. So that really crude explanation I gave for it is where that's coming from. And where tau is the excited population is how long until they relax down to the ground state. So we see that the non-adiabatic coupling is extremely higher in the methyl ammonium iodide rich surface than it is in the lead iodide rich surface. I'll get to that in a second, but for the most part, we'll talk about the excited state populations. So you can see right here that the excited state on average is significantly much huger than the methyl ammonium iodide rich surface, by 8 times as much, due to the it's hypothesized that the lower non-adiabatic coupling that is experienced in the lead iodide rich surface is contributing to the longer excited state. So why is it better to have a longer excited state population? Because the longer it is, the easier it is to be able to get that charge and keep it for yourself, or to be able to radiatively recombine and be able to get energy out. So for purposes of LED, the lead iodide rich surface is somewhat better, but I'll discuss right now real quick of why we see this phenomenon. So right here is a graph of the non-adiabatic coupling within time. So what they did right here, they took screenshots of the range of 2200 to 2500, because that's when the non-adiabatic coupling was found out to be at its highest peak. This is due to the methyl ammonium cations rotating within the cage and increasing, making it bigger, the lattice that's inside it. So these circles are depicted where they were at to begin off in the 2200, whenever they're seemingly low. There was no non-adiabatic coupling. So you see that the methyl ammonium over time will rotate up, and thus expanding the octahedral cage that they're normally found in, or on the edges. That's really hard to see. You see these points right here. They become flatter right there, so there's probably less distortion on the cage, and that's what's creating these higher distortions of non-adiabatic coupling. So conclusions, perovskites will hopefully one day open the door to a low cost, color tunable LED applications. 3D perovskites so far, they're not as suitable candidates as 2D perovskites are, and passivating the surface has extreme benefits to increasing photoluminescence from yield. Also, as an indirect cause of that, reduces the non-radiative recombination, and also do predict that perovskite LEDs to hit mainstream markets in the next 5 to 10 years. So, my acknowledgements, everybody here, everybody in the Kalina group, Amy, Dr. Krajewski, committee members, my undergrad, because he's cool, and then the question slide.
Okay, well, thank you. So you expired the questions of Ben. Because maybe getting. Levi, please. Yes.
So in your conclusions, you say perovskites will indeed open the door to low-cost, color tunable approaches for LED development.
Yeah.
But when you were speaking, you were not as definitive.
Definitive of?
That it will indeed, right? Because will indeed means it will happen,
Yeah.
and it's going to happen.
Yeah.
But then when you were concluding, you weren't as like, it's going to happen, you're like, it could happen. So it might be good to make sure that what you summarize is
Yeah.
on here,
Okay.
because someone might then ask you, how do you know?
Yeah.
right? And then
So I might as well just end up with conclusions of what I've already talked about.
no, I'm saying if it will indeed do it,
Yeah.
leave it, but then make sure you are confident and
Get up.
strong with your statement instead of acquiescing to it might work.
Yeah.
Time will tell. Does that make sense?
Yeah. No, it does. Thank you. Any other questions or comments?
So I had another side comment. You have an outline, right? And then you have introduction and you go through it.
Yeah.
And then you have background, and there's 2 slides in between background and quasi 2D perovskites.
Yeah.
Is it helpful for the audience if you have a outline and in between sub points it's very, very brief? So my question / comment, is it prudent to have background 2D perovskites introduction and so have those 3 slides if they're not really doing that much? Or in your eyes, do they do a lot?
They probably don't. Honestly, I didn't think so. I haven't had time to work on it as much as I'd like, but I probably should start doing it. Yeah. Yeah. This weekend's gonna be fun. That's a lot of work.
Okay.
Thank you for that comment. Any other comments, questions, concerns?
The slide before your non-adiabatic coupling
Yeah.
slide. Is there a relation, like, I don't know the best way to say it. So your top 2 figures, like, are they related to each other? Or could you infer one from the other?
Well, I guess they pretty much both mean the same thing. You see, the red peak is tensor, and the left image, well, the right one is also. Basically, it just means
What is the right one and what is the left one?
I guess I have it written right there. Time resolved photoluminescence.
Or I guess the thing I'm trying to draw a connection to is so in the left panel they give quantum yields
Yeah.
for their samples. So is there a relationship between quantum yields and the lifetimes shown in the right figure?
Yeah, higher. I guess higher. Quantum yield leads to higher lifetime.
Yeah, like I don't know who's like in the audience for yours, but that's kind of like a general
Assumption.
trend.
Oh.
Yeah, it's like you have longer lifetime, experimental lifetime, and it corresponds to higher quantum yields.
Well, I guess I did also mention that too, didn't I? Whenever I said that, P. Oh, I forgot the P, but anyways, right there the fluorescence increased by double. Basically, a little bit over double.
I don't know if it is that trend, and I know Aaron knows perovskites pretty well. I don't know if the longer lifetime necessarily means in all materials it will have a higher PL.
Or just
That's why I said it's a general trend. It's like if you just assume it's radiative and non-radiative recombination, if you just assume those 2 pathways, then you generally expect like your lifetime, like what you measure experimentally, that lifetime curve, the longer that is, the higher your quantum yields.
Huh.
So people in this field, that's like common knowledge, I guess they would expect.
Common knowledge. Yeah.
So that's why when you report quantum yields, you report lifetimes too.
Okay.
That's why people do that, because it kind of confirms both the measurements that they sync up.
Oh, okay, that helps. Yeah, I didn't really know how to explain that to that. Yeah, sorta. What I was gonna do too for the talk. I was just gonna have a little bit of notes here to help me out. I'm pretty sure the other second years they told me that's what they did too. So I'm just gonna have a little amount of data to always keep reminding me of what to say next time in case I forget. You know what I mean? So that's what.
But if you do that, make sure you stand behind your screen.
Which well, I was gonna look over it every now and then, just not just stand behind the podium either all day. You know what I mean? Trust. But yeah, I'll just use that as a helpful reminder.
Yes, you can print it in a page and put it on the table if you need. You can take a look at sometime.
Okay, yeah, that too. Yeah, because I don't want to put captions for everything just to say that, oh, this is a time result for the luminescence. You know what I mean? I forget. But yeah, I still have like a couple more papers to cite.
And also, if you think you don't remember what the result it is,
Yeah.
you can just put a one small captions in every image. Below that one, it will help you to know what is it.
Just like that, time result for the luminescence, just throw that in there. But that helps too. Yeah, because that's what I've been mostly using these for, just to
Yeah,
remind
you need to
myself.
find
that
out your companion where how can you do that.
they're- Okay, yeah, of course.
Well, Eric would definitely ask you that question.
Which
Like
one?
the relationship between con yield and lifetime.
He would.
Yeah, he would definitely ask that.
So,
Yes, everything.
looking at the PL, the line width is pretty broad. Right or wrong?
PL right here.
Not the.
This one?
Yeah.
Pretty broad. Oh, so you're talking about this intensity right here?
Yeah.
Yeah, it's analogous to a green emission, or it's
So
the
for
green wavelength.
LEDs, do you want it broad?
Well, doesn't it go back to RGB? The
Yeah.
broader the better. Well,
Ooh.
in that
Powers
range
one.
of the green, blue, red,
No.
you want them sharp, not broad.
So what would happen every time a LED emit all lights?
It'd
You
be
will get
changing
just a white
colors.
light every time, right?
Oh,
Yeah.
You don't want that.
don't want that. Oh, that's good too.
And also, what about brightness? If you get this,
Brightness.
what would happen if in brightness? In case of brightness,
If you get a peak like this.
very white peak, yeah.
What would happen to brightness? It won't be as bright. Guessing.
By the way, it's logarithmic scale for your y-axis.
This one is.
Yeah. So it's not that wide.
Oh. That's not just a ratio. I thought it was just a ratio. 'Cause that's what that's
It's
what the
logarithmic.
division. Oh, so it's actually sharp, extremely sharp. Oh, extremely. Oh,
So the tiny difference between red and blue
yeah,
is relatively large
yeah. Oh, so.
because it's logarithmic.
Oh, okay, so. Right.
See, and I trapped you in a statement that was incorrect, but
Yeah.
looking at the data,
How'd you know it was logarithmic though?
because I looked, and the y-axis is not linear.
Like, look at your scales.
Look at the ticks.
I was wondering what I was looking at the ticks. I didn't know what that was. I was like, is that just a mistake, or I'm just gonna go with it? But
No,
yeah.
so it's logarithmic,
Okay.
which means that is relatively short.
Okay. So.
But if I didn't know if I didn't notice that and I just thought, oh, it's very broad, then it would be a pretty big difference. And to point out on this one too,
Yeah.
these are also logarithmic.
So the really so the huge differences.
Yeah, so that's why if you look, can you go back to the one
Yeah.
before the blue sheets? This one. So if you look, the green is not that much bigger. But if you now look at the PL intensity,
Yeah.
it's massively different.
Oh yeah. Oh okay. Yeah. I should have been able to tell that myself. So one thing. What if they ask me why is that negative?
It's noise.
It's noise. Did you say that? Okay. Yeah, I was looking at that. I was like, how can you get intensity that's negative? You know, but it's just noise. Okay.
Right? It's experimental. And it's on the low end of the log.
In the logarithm scale, there is no negative.
But
You
it
can-
might
you
not
can-
be zero.
You can take everything is a little above zero if you apply logarithmic scale. Otherwise, it will give you.
Yes, but I don't think it starts out at 0. They don't have the numbers.
That's right.
So when you read through, make sure you look at the data and know how they plot it,
Okay.
because you can easily get trapped.
Look at the data. Yeah, especially if I get experienced researchers like Rogers.
Oh yeah.
I know Rogers loves this stuff, doesn't he?
Yeah.
Thank you. Yeah, I'll look into that, and then I'll probably read the supplemental data to this stuff again because I couldn't find it, but Javed said he found this, so I gotta try harder.
So what's your strategy? What are you going to do during the weekend? Just eat, sleep, relax.
I wish. Maybe next weekend, not this one.
But what are your measures against the provocative questions of the committee and audience?
Provocative?
Like the trap questions. Of course, you will go through, polish, rearrange in logical sense, collect comments and implement them. But who knows? Will it help to address the questions? There will be some unexpected questions.
Yeah, no.
So what is your strategy?
No questions, please.
Just tell them to refine their question. Keep them like talking.
Make them
until
answer
they
make them answer half their question.
Yeah, that's one strategy.
Okay.
It's one strategy. And another one, sit in silence and write down questions which you either fear or you again want to ask to yourself, or what you remember from the session. Hopefully it will be recorded, you can watch it again, and prepare slides where title of slide is a question and body of a slide is an answer. But do not show them. Keep them to under the question, and then if you someone asks you, you know, oh, you wanted to ask this one. Here's the answer.
Okay.
I can read minds. I knew that you would ask this.
Okay.
Because there will be a little stress, and if you sit in peace at home, and you probably prepare better.
And if your talk is 25 to 30 minutes long, you will get a long time to get it.
Yes.
Yeah,
If
I know.
that happens, you're gonna have an hour of questions.
No. Feel all the time. Make your 60 minutes long, so that the chair will kick you out of podium and will kill anyone who asks you questions. Make it lengthy. If you fear questions, if you love questions,
Make it lengthy. Okay.
if you love questions, be short and let discussion to go.
I guess I might go back to what Levi said and just try to find like experimental of RGB. So I already talked about G.
But don't talk unnecessary things. Don't talk about irrelevant things, irrelevant stuff.
Okay.
Again, do not hide your achievements. If you are reading some papers, cite them.
Like
Yes.
talk about it.
Mention that it is not your fantasy. It is something you learned from specific paper.
Okay.
And it might be good, so if you have 15 papers, right?
Yeah.
You read through them. One bullet, what the conclusion was, right?
Yeah.
Then what you could possibly do is say, I have one bullet, why this is important. Once I go through my introduction, I have set what I need to do, and then you could order your papers into a logical flow from one to the next, using that one statement. Say, this one has good quantum yield, right? But it does not have the right color, right? And then the next one might be, it has good green, and it has good quantum yield, right?
Okay.
So if you have a logical flow, instead of going through all the details when you're preparing the slides, that might also help. Does that kind of make sense?
Yeah. When I make the slide, just ask myself what the conclusion is.
Yeah, and then that would also help with the transition, right? So if you have one paper that is on a specific topic,
Yeah.
then the next paper that builds off of that topic,
Okay.
you can be like, this research group did blah. Off of their conclusions, this group then went further and did this.
Okay.
Right? So then it's more flow instead of here you have experimental data. I'm going here now, right? So there's a huge disconnect. And if you order it correctly, your work will be infinitely easier as a speaker versus experimental data.
Yeah.
Shoot, what do I need to say now? What do I need to say? Oh, theory. Okay, there we go. I'm done. Move on. Does that make sense?
Yeah.
So by now, Levi is absolutely correct. It is the weakest, it was and it still is the weakest part of your talk.
Yeah, my transition.
So, yes, you are progressing really well in absorbing a lot of material and understanding it, but setting it up in logical, and even setting it in logical connection is fine, but the transitions are very chopped.
Okay.
So if you do not have time, you will be super busy, but if you have time, sit and answer yourself, what is the logical connection between each slide for each transition?
Okay.
Because it is, by now, it is the weakest part. Okay. Absence of transitions. More questions? No? Everyone is happy? Okay, but thank you, Daniel. So everyone is invited, to, if time allows, to come on Monday at 4.
Yes.
LED 209 and support Daniel.